the goal of this talk is to get you excited. There's a lot of cool things to do in this space, and people are not paying attention. Okay, so what am I going to talk about? I'm going to talk about the RLIBM project. Alternative title is like how we built the world's fastest math library. And who cares about math libraries? Everyone uses math libraries, right? Like some people do care there. But whether you like it or not, everyone uses a math library. Some people hated calculus. They want to forget about like all the elementary functions. What do these math libraries contain? These math libraries contain elementary functions, which are functions of a single variable involving addition, multiplication of trigonometric functions, logarithms, and polynomials. They're used everywhere. So it's like plumbing, right? Everyone relies on it. No one worries about them. And you need a plumber, you have an emergency. Okay? So if you are using machine learning, e power x, right? Sigmoid function. Natural language processing, speech processing. We just had a talk on processing beats, right? Like e power x plays a prominent role there. So it's all there. So unsurprisingly, you have implementations for these functions. Where do you find them? In math libraries, libm, like -lm when you compile your code, right? They're all automatically included. Okay? But unfortunately, they're all wrong. Okay? So I'll tell you what wrong means. Okay? So I come from a formal methods world, like wrong means, oh man, everything is failing, right? So one of the issues with having wrong libraries is non-portability. You have your fancy GPU, you run your training model, it produces some results. You just port it to another nice GPU that another company has brought out, you get totally foobar results. Imagine you are the developer trying to debug it. What nightmares you will go on. Again, like Santosh is another guy just talking about random things, right? If you don't trust me, there is a nice keynote by Ali Rahimi. He's a machine learning researcher at NeurIPS. And in the middle of the keynote, he has a code. This is a production bug report filed by one of his team members. Oh, I changed the rounding mode in my training to round to 0. Why would anyone use round to 0? It's attractive for performance. And the accuracy dropped to 25%. Okay, the model had a reasonable accuracy, 85% or so, and now it's 25%, doing nothing, just changing the rounding mode. So this is where, like, if you care about portability, if you want to make your code robust, like there's a lot of interesting things to do in this space. So effectively, we want to build correctly rounded elementary functions. And as Zishan alluded to, I come from the compilers and formal methods world. You don't wake up one day and start working on numerical analysis, right? Let me tell you a story about how I got excited about this area. So about 10 years ago, we had been working on proving the correctness of compiler optimizations. Compilers are large pieces of software, million lines of code. Everyone relies on them, and there are bugs. And it's a fact of life, like bugs are always there. But you don't trust, you don't believe your compiler is wrong, right? Sometimes if something is wrong, you trust, oh, my code is wrong, let me fix it first. But compilers do a lot of crazy things, and they're wrong. So we wanted to address it. We built formal semantics of the LLVM compiler in the Coq proof assistant in collaboration with my advisors at Penn, Steve Danzavec and Milo. And then we realized like it's very difficult to get traction from developers. So what did we do? So in collaboration with my student and a few other collaborators at Utah, John Reger and Nuno Lopez, we built this domain-specific language called ALI. So effectively, what was it? Like, what was ALI? ALI was a small DSL where you would specify your optimization in this DSL, and we would automatically prove its correctness using theorem provers, first order logic theorem provers. We would generate SMT conditions and give it to Z3. If it's correct, your compiler optimization is correct. And today, many LLVM developers use ALI to check the correctness of new optimizations. Okay? So this was primarily like people of local rewriting rules. And my student was like, okay, we were just focusing on integer optimizations. What about floating point? And compilers like compiler optimizers fall into two categories, right? Like one, I don't want to do anything with floating point. I just want to like, okay, IEEE says this, like I'll just do that. Even when they do that, they make mistakes. So we had a snippet of alive called alive FP, where we wanted to check bit precise optimizations. Is the value produced exactly bit to bit same? Okay, and IEEE compliant. And we found bugs. And if you don't know floating point, there are two zeros, +0 and -0. And one of the LLVM optimizations was changing the sign of 0. Okay, so my student told this to his lab mate, and he said, who cares about sign of 0? But William Kahn, a Turing Award winner, has a nice article which says if you change the sign of 0, it causes discontinuities in branch cuts. So we filed this bug, it was immediately fixed. Okay? And then there are the second class of compiler optimization designers. They have this demonic mode called fast math, or I would call it incorrect math. Okay? So what do? It considers any real identity as a floating point identity and optimizes code. Okay? So associativity is not true with floating point. Okay? But when you invoke fast math, they treat, floating point arithmetic is associative. It's very important. You should not blame them, because like you can't do parallelization without associativity. Okay? So there is this fast math mode. And this is the advantage of having curious students, right? My student then was taking a machine learning course. And he had a nice data set. He was learning some training algorithm, a support vector machine training algorithm. He implemented the algorithm in C++ and then trained it on a curated data set. He got a reasonable accuracy. And then out of like curiosity or magic, I would say, he turned on fast math optimizations. And the accuracy tanked significantly. Doing nothing, training for the same number of iterations, same amount of time, the accuracy drops. And we wanted to debug it. And as I said, what is the issue with portability? Small errors getting magnified, right? So debugging is a nightmare. Okay? So we looked around, who can help us, right? Like, are there debuggers available? There was none. So we built our own. Okay? So what debugger would be useful? So we said, let's do a shadow execution. What do? We have your regular floating point program. You have your another program where we execute it with real numbers, simulated with MPFR, which is very slow, but like we do lockstep execution with real numbers and we compare. Where do the Oracle program and the floating point program diverges? Okay? And it turned out the divergence happened in the math libraries. You would call a math library and it produces a very small error in the result, and it gets amplified with cancellation and various other things. The end result is crashes. Okay? And we had like lots of nightmares debugging it, reproducing the same bugs and other aspects of it. Okay, so this is what got us excited about looking at this problem. Okay, math libraries are producing wrong results. This is not a new problem. Why aren't people producing correct results? Okay? So now, what is a correct result? I've been talking about wrong results, correct results. What is a correct result in the context of a floating point, right? You have a number line. Here I'm showing you the number line. You have infinitely many real numbers. You cannot represent everything with floating point. You only represent finitely many real numbers with a floating point representation, which is a finite precision representation. So here V1, V2, V3 are values that are exactly representable with a floating point. Okay? And now you call an elementary function, okay, a math library function, lan of x, right? So it's called elementary because it produces an irrational value. Most likely, in 99% of the case, this value will not be exactly representable in your floating point representation. So now what do? You need to round the result to the nearest floating point value. And there is a rounding mode which specifies how you do the rounding. The most commonly used rounding mode is round to nearest ties to even. Okay? So what did you do? You take your favorite algorithm for approximating lan of x. Do it with real numbers. And then do the final rounding to get the floating point result. And here V2 is the correctly rounded result. Okay? If your library produces the correctly rounded result for all inputs, It's a correctly rounded library. Okay? So why is this useful? It is useful because it enhances portability. Like for example, long ago, when IEEE standard wasn't around, every hardware vendor had their own implementation of floating point. Porting code across multiple processors was just a nightmare. Okay? So by standardizing it, you can make your make the life of developers easier. So ideally we want a correctly rounded library. Unfortunately, the conventional wisdom is generating correctly rounded libraries is very expensive. And that's why IEEE standard does not mandate correct rounding for elementary functions. It mandates correct rounding for primitive operations, addition, multiplication, subtraction, division, and square root. Okay? So now, why aren't existing approaches producing the correctly rounded result? So even before you go there, we need to identify how do people approximate elementary functions. Okay? So this is where like you'll have a brief taste of real analysis if you have taken it, but you don't need to know anything to understand the talk. Okay? So everyone approximates elementary functions with polynomials. So there are classic results from real analysis, Weierstrass approximation theorem, which says that if you have a continuous real valued function over a small domain, you can approximate it with a polynomial. Okay? So everyone approximates the real value of f of x. As I show in the slide, such a polynomial approximation is feasible only if you do it over a small domain. And what is the range of a 32-bit floating point? 2 to the power of 128 to 2 to the power of minus 149. And you cannot do polynomial approximation over such a large domain. So the first step in any elementary function implementation is to do range reduction. So what is range reduction? You are reducing an input which belongs to the domain 2 to the power of 128 to 2 to the power of minus 149 to a smaller domain. What should this smaller domain be? Ideally, like for LAN, it should be 1 to 2 or like 1 to 1.33 or something. Okay? So how do you do this? So you use mathematical properties of logarithms or the elementary function of interest, and you do this. Okay? So you approximate the real value of f of x, and then you reduce the input to a smaller domain. And now you do polynomial approximation over the smaller domain for the reduced input. And eventually you get the result for the reduced input. What do you need to do? You need to compensate the result that you get to produce the result for the original input. So this last step is called output compensation. So if you forget all the jargon, like the thing you need to remember is everyone approximates the real value, and then they do range reduction, and then they evaluate the polynomial create a polynomial approximation over the small domain, and then they compensate the output, which is called as output compensation. All these 4 steps are done using floating point. Okay? So they're going to have some errors. Okay? So now, why do they produce wrong results? So I'm going to pictorially represent what happens with an existing approach. Let's say the real value of your elementary function is very close to the rounding boundary. Okay? In this case, in the slide, v1 and v2 are 2 representable values in your floating point representation. So what is the rounding boundary with respect to round to nearest ties to even? It's the midpoint. If a real value is very close to the midpoint, any small error that you will have will make it produce the wrong result. So the freedom that the polynomial generator has is the gray box that I show in the slide. Okay? So now recall, what did I say? You have to do range reduction, output compensation, and polynomial evaluation in floating point. All those is going to have some error. Okay? So any such error is going to push the value outside and eventually resulting in wrong results. Okay? So the key takeaway I want to remember is everyone is approximating the real value of f of x. So our f if any, or our key insight is, why are we approximating the real value? In the RLIBM project, we make a case for directly approximating the correctly rounded result. Why? You are not worried about the real value. You only care about the correctly rounded result. Directly approximate the correctly rounded result. Well, you're thinking, man, are you fooling us? You said like you want to approximate the correctly rounded result, but you know the correctly rounded result only when you know the real value. How do you know the correctly rounded result? So our key insight is when you cannot solve a really complex problem, split the problems and solve smaller parts and do it well. So we split the problem of generating efficient implementations into two parts. The problem of generating the oracle, which tells you what the correctly rounded result is for each input. Okay, this can be slow, and like a lot of people, like this is not, this, as Zishan was alluding to, this is a problem that people have attacked for centuries. Okay, so there are good oracles out there, built on the shoulders of giants, right? Now we know that once we know the oracle, what do we want? We want our models to run faster, right? So we want efficient implementation that produce correct result. So you design efficient implementations by directly approximating the correctly rounded result. Okay, the focus of the RLIBM project is, given an oracle, let's generate polynomial approximations that produce this result efficiently. Okay, so first insight, directly approximate the correctly rounded result. And this is where like thinking like a computer scientist actually helps, right? I do have a lot of math background, but I had to do this, I had to forget some of my math background and think like a person who would implement stuff. Okay, so now, cool. So we want to approximate the correctly rounded result. But that doesn't solve, right? But the key insight, the next insight that we had is, if you have a correctly rounded result. So let's say we are designing a correct math library for a 32-bit floating point. How do we, in which representation do we implement the library? We would implement the library in double precision. So there are a set of real values. There is a range of real values around the correctly rounded result in the double precision. You produce any value there, it will round to the correctly rounded result with a 32-bit float. This is the freedom that you have. Okay? So this gray area is the freedom. So there's a range of values. In this case, V1, V2, V3 are 3 floating point values. V2 is the correctly rounded result. What is the rounding boundary between V1 and V2? The midpoint. And what is the rounding boundary between V2 and V3? The midpoint. So the region between the two midpoints is the freedom that you have. You produce any real value there, it will round to the correctly rounded result. This is the freedom that our polynomial generator has. Okay? And if you recall the figure, this freedom is much larger than whatever you had with a minimax polynomial. And this is precisely why the RLIBM implementations generate really fast implementation. Like more freedom means you can use lower degree polynomials, which implies speed up. Okay, so directly approximate the correctly rounded result, and then there is a range of values around the correctly rounded result, which produces such that like if you produce any value in this interval, it produces the correctly rounded result. Now, how do we generate it? The insights are fine. What is the methodology? Okay, so our methodology is, we have an oracle, we have the representation and the elementary function that we have for each input, and a given elementary function and a rounding mode. We would use the oracle and compute the correctly rounded result. Okay? And then we would compute the rounding interval for the correctly rounded result. And the gray boxes on the figure are the correctly rounded result. Once you have this, you don't care about the correctly, interval is whatever you care about. Now we want to generate a polynomial that satisfies all these intervals. Okay? What is a polynomial? We know the inputs, x1, x1, x2, xn, right? And what we don't know is the coefficients of the polynomials, c0 plus c1x plus c2x square. So the task is to generate these coefficients. Okay? So what does each interval specify? When you evaluate a particular point, the result of the polynomial should be greater than the lower bound and should be less than the upper bound. It's a linear constraint. So effectively, what do we have? We have a system of linear inequalities, okay, for a given degree. Now, another well-studied problem, linear programming. So the very good solvers out there use an LP solver out there and encode this into a system of linear inequalities, give it to the LP solver, it generates the coefficient, and there you go. You have a polynomial that satisfies all the points. Okay? This is the first insight that we had like 4 years ago. And this was our Popple paper where we summarized this result. Okay, what do we have? Directly approximate the correctly rounded result. There is a interval of values around the correctly rounded result, then frame an LP problem, and you can generate correctly rounded implementations. So life would have been amazing if there was only one representation and one rounding mode. But today, everyone is designing their own representations, trading off the dynamic range or the precision. And if you're still not convinced, just 2 days ago, a consortium of NVIDIA and Intel researchers released an archive paper, FP8, 8-bit floating point standard for accelerating machine learning workloads. Okay? It's a cool paper. Look at it, like all the trade-offs that is required to accelerate machine learning. So our next question was, can we design a single representation, a single polynomial approximation that produces correctly rounded results for multiple representations and multiple rounding modes? Why is this attractive? You are a library designer. You don't have to design a library for each representation and each rounding mode. Okay? So then you may be thinking, what is the largest representation that anyone uses? Doubles, right? Like right now, for most practical purposes. Why don't we use the naive solution? If we design it once for 64-bit, are we done? So let's say I designed a correctly rounded library for doubles, 64-bit type. Now, like what are people doing? Just shrinking precision, right? Like I'll just repurpose this library for everything. So what would you do? Let's say you have a 32-bit float. You would create the input. You have an input in 32-bit float. You would promote the input to a double precision. So every floating bit, every 32-bit value is representable in 64-bit. Okay? And then you call the 64-bit library. You would get the result in, you would get the output in double, and then you truncate it back to float, round it back to float. Okay? How many of you think like this will produce the correct result? Yeah, everyone presuming I have something to say. So this is wrong. This doesn't work. That's a naive solution right there, right? So why doesn't this work? This doesn't work because of double rounding error. What is a double rounding error? So I'm going to demonstrate it here with a cartoonish figure here. So you have 64-bit doubles and you have 32-bit floats. The most important thing is look at this bottom row. You have a 32-bit float. There are 3 float values there. And there are a lot more 64-bit values between 2 adjacent 32-bit values. But just for exposition, I'm just showing few values here. So the star is the real value produced by your elementary function. And now you have a correctly rounded double library. So this is a correct result from the perspective of a double library. Okay? And now if the value is very close to the midpoint, you rounded it. And now if you take this double value, it's exactly at the midpoint. And if you round it to float, it produces, it rounds to the red box. But if you look at it, this value is less than the midpoint. It should have rounded it to the box on the right. So there are two roundings happening. The first rounding is when the when the designer of the elementary functions designed it, right? Designed the library. So there was one rounding. The second rounding happens when you take the double value and round it to float. And this is very common. So if you want to generate a single polynomial approximation that works for multiple representations, you need to make double rounding somehow innocuous. Okay? So how do you make double rounding innocuous? So this is our next magical result. Like this is the advantage of having great students, right? Like who come up with like really amazing ideas. So the real value, like you have to maintain certain information about the real value such that the rounding decision is not changed in the presence of double rounding. So what information do you need to maintain about the real value? So there are 3 pieces of information that you would want to maintain. Is the value less than the midpoint? Is the value exactly at the midpoint? Is the value greater than the midpoint with respect to the target represented? If you maintain these 3 pieces of information exactly, you can make double rounding innocuous. Okay? So this is the key insight. But what is our magical solution to address it? So if you want to create a correctly rounded library for all representations up to n bits, okay? Create a polynomial approximation, a correctly rounded polynomial approximation for n plus 2 bits, 2 additional bits, with a non-standing rounding mode called round to odd. And I'll describe what round to odd in a minute. And if you magically double round this to any representation from 1 to 32 bits, it will produce correct results. and all the 5 rounding modes in the standard. Okay? So now there are a lot of things to parse. The first thing to remember is if you want to generate correctly rounded results up to n bits, create a library with 2 additional bits with a round to odd mode. Now what is a round to odd mode? Okay, it's a non-standard mode. People have looked at it, like if you read a paper titled "What Every Computer Scientist Needs to Know About Floating Point" by Goldberg, right? So there is like he references to it when he is talking about casting, converting a binary fraction to a decimal fraction. And why haven't people used this round to odd mode for elementary functions? Because people have been obsessed about real values, they've never been thinking about specific rounding modes for generating libraries. So in contrast, in the RLIBM project, since we directly approximate the correctly rounded result, we can directly approximate the round to odd result and still be, we don't need any additional numerical analysis. So now let's walk through the intuition. So what is round to odd? So the round to odd mode is explained in two sentences. First, if the value is exactly representable, it rounds to this value. Okay? So if the value is exactly representable, it rounds to the value, that value. If the value is not exactly representable, then it rounds to an adjacent value whose bit pattern is odd. Okay? So there are a lot of things in the slide, but let's go back and step back and give you a very pedantic example. Let's say we live in a world where we just have integers, okay? And you produce a value 9.6. Okay? We just have integers. You produce a value 9.6. You need to round. Now 9.6 is not exactly representable as an integer, so you need to round. Where do you round to? In your typical usual world, you would round to 10 with round to nearest. With round to odd, you would round to 9 because 9 is odd. Okay? So this is round to odd mode. So just to reinforce this, let's say you have a value 10.3. 10.3 is not exactly representable, so you would round to 11 because 11 is odd. So the round to odd, if the value is exactly representable, it rounds to that value. If it's not exactly representable, it rounds to a nearest value whose bit pattern is odd. Okay? So this is round to odd. Now round to odd makes double rounding innocuous. Why? Okay? So let me illustrate this. So let's say we are designing a correctly rounded library that produces correct results for all representations up to 32 bits. So then we need to create a polynomial approximation for a 34-bit library. So I'm going to here in the second row I'm showing the 32-bit values, and in the first row I'm showing the 34-bit values. Between two adjacent 32-bit values, there are 3 34-bit values exactly representable. So now irrespective of whether this bit pattern is even or odd, any value that is representable in 34 bits will be even in a 34-bit representation. Okay? So this will be even, this will be odd, this will be even, this will be odd, this will be even in a 34-bit representation. So now the key point to remember is what are the key things? The midpoint is even in 34-bit. And any value less than the midpoint, it rounds to the odd value with round to odd. So it rounds to this green value. So now if you double round it later on, it will round to the correct floating point result. Okay? So the round to odd preserves this information, the 3 pieces of information that is required to correctly round any values. What are those? Is the value less than the midpoint? Is it exactly at the midpoint? Is it greater than the midpoint? So the proof is a bit more involved. I don't want to burden you with like the details of the proof, but the key theorem that we prove in the paper is take a real value. To round a real value to any representation, there are 4 pieces of information that you need, like which we call as the rounding components. And what we show is the round to odd mode preserves the exact same rounding components for rounding any real value to any representation. Okay? So the end result is, if you want a polynomial, if you want an approximation that produces correct results up to n bits, create a library with n that produces correct results for n plus 2 bits with a round to odd mode, and it magically produces correct results for all representations and all 5 rounding modes. So now the question is, how do we go about creating this library, right? So we exactly use the RLIBM approach. So you have an oracle. In this case, there is no oracle which gives you 34-bit. We built the oracle for producing 34-bit round to odd mode. For each input, we would compute the correctly rounded round to odd result. Okay? And then we generate the rounding interval. So the odd interval, so that every value rounds to the correctly rounded odd result. And then the only issue that you need to worry about here is if the value, if the result of an elementary function is exactly representable in your representation and is even, its odd interval is a singleton. Generating singletons is challenging. But fortunately, this problem of identifying singletons in the context of elementary functions is well studied. So what is a floating point input? It's a rational value. If it's exactly representable in a floating point representation, it means it's a rational output. So what we are looking for is you have an elementary function which takes rational inputs and produces rational outputs. And there are some fantastic results from real analysis which we use. So just to give you an example, like let's say we are computing log x to base 2. So when I is an integer and even, then log x to base 2 is exactly representable and it's even. So it will be a singleton. So we use bit vector operations to compute such results and remove the such singletons. Okay? So once we remove those singletons, we are left with like odd intervals. We generate a polynomial for them. And it produces correct results for all inputs. Okay? So what are the 3 takeaways I want till now? There's one more takeaway, but like the 3 takeaways till now: directly approximate the correctly rounded result. Then there is an interval of real values around the correctly rounded result. Frame an LP problem. And if you want a single polynomial that works for multiple representations and rounding modes, create a polynomial approximation for 2 additional bits, n plus 2 bits with a round to odd mode, and it magically works. Okay? So the last thing that I have been talking about is how do we generate this, how solve this LP problem. So what do we have? We have a single polynomial that works for all representations. And if I generate it for 32-bit float, it includes the 16-bit float, B float 16 from Google, NVIDIA's 19-bit TensorFloat 32 representation, half precision, and all other representations, many other representations that people are worried about. So one of the questions I got when I gave this talk a year ago was, this is all great, like it's amazingly good, but you're making like my B float 16 library pay the cost of 32-bit float. Can you make it better? Again, this is why you meet people and like get feedback, right? They ask questions and I think. So can we do better? And this is where we introduced this notion of progressive polynomials. So you have a single polynomial that produces correct results with a round to odd mode for all inputs and multiple representations. If you care about a couple of representations, let's say B float 16 and TensorFloat 32, you just use the first few terms of the same polynomial. It produces correct results for B float 16. And additional few terms, it produces correct results for TensorFloat 32. Okay? So in our formulation, how do you do this? Like you just discard the higher order terms when we generate the constraints. So it just results in more constraints in the LP formulation. So the entire polynomial produces correct results with a round to odd mode. And then if you just want correct results for B float 16, you just don't include those terms in your constraint generation. So such a polynomial which has this property is a progressive polynomial. Okay? So the only challenge now is you have more constraints. With 4 billion inputs, you already have 4 billion constraints. Now on top of it, you added like additional constraints for B float 16 and TensorFloat 32. Now we want to solve an LP problem with 4 billion constraints. How do we do this? Okay? So we are relying on LP solvers, right? So to solve them, even though LP problems have been well engineered, they can't solve 4 billion constraints. They time out. Okay? So we had to be clever. So the first observation that we do is our LP problem, the linear program that we generate, is a linear program of small dimensions. Even though we have 4 billion constraints, how many terms do we have in the polynomial? Very small. We are not looking for 1 billion degree polynomial, right? We are looking for a polynomial of degree 5 or 6. So the number of terms are pretty small. So our linear program is a linear program of small dimensions. Okay? So we have an efficient algorithm to solve them. So what is the key idea? So if your linear program is full rank, okay, that means like there are k constraints that satisfy all other constraints. There exists like k critical constraints. If you just identify them, it will solve the entire problem. Okay? So now how do you identify these k constraints from 4 billion constraints, right? This is where we employ a randomized algorithm inspired by a classic result from 95 from Journal of the ACM, Clarkson's method. Okay? So I'll give you the sketch of the randomized algorithm. Okay? So we have all these 4 billion constraints, and we are going to do sampling. We are going to assign weights to each of these constraints. Okay? So initially, all these constraints have weight 1. Okay? So the first step is just uniformly sampling some constraints. How many samples how many constraints do we sample? If the polynomial has k terms, we sample 6 k square constraints. Okay? So it's degree 6, let's say the 6 terms, 6 times 25, which is 150 constraints, and any LP solver can solve it. So we are in the realm of modern LP solvers. So we sample these constraints and generate a polynomial. Okay? So the sample is satisfied by the generated polynomial, and it may not satisfy many other constraints in your universe. So we evaluate and test it out, and it turns out all the red constraints are not satisfied by your samples. What do? We double their weights. What is the goal? In the next sampling, we should increase the probability of picking them. So we do weighted random sampling. Okay? So now we discard the sample and repeat the process. So now we double the weights and we resample again. Now some of the constraints which was weights were double will now be in the sample. Okay? So we repeat the process and check it violates some other points. And now double their weights again. And in the next sample, when we do weighted random sampling, we pick a new sample and repeat this process. Eventually you end up with k constraints in your sample, and it satisfies the entire universe. So in a paper, we provide the proof that this randomized algorithm terminates in 6k log n iterations in expectation. So this is a worst case bomb. Okay, so randomized algorithms, like designing a randomized algorithm is easy, right? Providing the bounds is the hard part. So the proof is a bit involved, but like it's easy, still it's easily doable. So the end story, in practice, we see this much more effective, like we don't need all these iterations. This is a worst case bomb. So what do we have? Now we know how to generate, like insights behind generating correctly rounded libraries. We know how to solve the problems effectively. And this is all nice stories that I have been telling you for the last 30 minutes, right? At the end of the day, what do you care about? Does it work? Okay? So we built a collection of 10 functions on this slide, but this is like PapersWeLove, right? I'm just presenting the 4 papers as part of it, but like the project has like 19 functions, including all the trigonometric functions right now. So a single polynomial produces correct results for 805 different configurations. Okay? And for all inputs, 2 power 32 inputs with a floating point representations. And just to give you a flair for how others fare, these are like libraries that have been optimized for decades. So not just a couple of years, right? Like they produce wrong results. Okay? And even correctly rounded, like RLIBM is a correctly rounded library developed at India. It's a correctly rounded double precision library. But because of double rounding error, if you take that result and round it to any other representation, it produces wrong result. It does not produce wrong results. So the moral of the story is RLIBM functions are correct. So now the next question is, what are we paying in terms of performance? Right? So now in this slide, I'm going to show you what is the performance speed up with RLIBM functions. So the line at 1 means we are as good as the baseline library. So the baseline library is Intel Math library, very well optimized by like amazingly respected people. So Intel library has 2 modes. One, you can approximate float functions using float itself. And you can approximate float using double precision. Okay, so the approximating the float functions using double precision reduces the number of wrong results, but still not correct for all inputs, but reduces the number of wrong results. Okay? So compared to Intel's float functions, we are about 30% faster on average. And when you look at double functions, we are about 50% faster. And these slides are like 1 year old now, because like all the papers, like we are talking about published papers, right? So there's a lag of 1 year. If you go and like download my GitHub library and like test it out, your results will be more like 2x. So I would encourage you to test it out. So we are like faster. So the moral of the story, like we are not only correct, but also fast. That shows the value of the idea. So it's just like 4 of us building this library. So I don't have an army of engineers building this, right? So in contrast, many production companies have teams of 30, 40 people building these libraries. Imagine how much faster we can go if we had a team of that size. So now the last thing I want to demonstrate is like how do we compare to correctly rounded libraries, CRLIBM. In contrast to CRLIBM, we are close to 2x faster on average across all functions. Okay, so all this is great. Like even with a small team, we have been pushing these functions into mainstream. So we have been collaborating with the LLVM developers and pushing some of these functions into the new LibM that the LLVM is developing. So 5 of these functions have been incorporated into LLVM's new LibM, which are correctly rounded for all rounding modes. Again, Tu Lee has been instrumental, and Paul Zimmerman from France also has been helping us out in this effort. So I think like if we are successful in the next standard, which is supposed to come out in 2029, we want to give enough evidence for IEEE Standards Committee to mandate correct rounding, at least for 32 bits. Okay, so to conclude, what are the 4 takeaways that I want? 1, directly approximate the correctly rounded result. There is an interval of real values around the correctly rounded result. Produce any value, you're good. And if you want a single polynomial that works for multiple representations and multiple rounding modes, create a correctly rounded implementation for a representation with 2 additional bits, n plus 2 bits, with a round to odd mode. It magically works for all representations up to n bits. Okay, so again, the goal of this talk is to encourage a lot of you to contribute to this area, and let's make our systems more robust. And I want to thank National Science Foundation for funding really like crazy ideas and enabling us to explore this space. And thank you for your attention.